Welcome to the first video accompanying Chapter 3, titled Changes in Our Perspective. In this chapter, we're going to focus on the history of science that led to modern astronomy, how the history of physics contributed to modern astronomy, briefly, in the final part of this chapter and these slides. We're going to talk about the nature of science and the hallmarks of science and the scientific method a little bit. And mostly, though, build on how we got to the point today in terms of the models and the assumptions and testing those assumptions in the science of astronomy. So let's get to it with a little bit of ancient history. All right, so some opening questions. In what ways do all humans use scientific thinking, and how is modern science rooted in ancient astronomy? So, scientific thinking is based on everyday ideas, observations, and trial and error experiments. Okay? So, that's it. It's a simple statement. Many of our current systems have their roots in the achievements of ancient astronomers. Timekeeping, tracking of the seasons, the idea of a calendar that repeats every year, following and monitoring the lunar cycles, following the planets and stars and their repeated cycles, predicting eclipses even. Okay? So here we're looking at an example where the ancient people of Central Africa, and this was 6,500 BC, so over 8,000 years ago, could predict seasons from the orientations of the crescent moon. Okay? So they saw a correlation, a pattern between the crescent moon, and they knew the rainiest season corresponding to the crescent moon that was flat. And you might think to yourself, well, crescent moons don't look like this. Don't crescent moons look more like this? Well, that's because when you're at northern latitudes, okay, so above the equator, then that is what crescent moons look like. But due to a change in perspective, when you are at the equator, crescent moons are the bottom of the moon and only tilt, as we can see, a maximum of 30 degrees horizontally. So that's definitely a testament to all the things that we talked about in the previous lecture about observing eclipses and observing phases of the moon. Your location on the planet, the location of celestial bodies, in this case the sun and the moon, really matter. And the reason, by the way, the simple explanation of why in equatorial regions like Central Africa, the crescent moon is mostly flat, as shown here, and it is mostly vertical in the northern hemisphere, or the north of the northern hemisphere, can be explained by axial tilt, the 24.5 degrees of axial tilt of Earth relative to the ecliptic plane. And the fact that furthermore, that the moon's orbital plane is tilted 8 degrees towards the ecliptic further compounds the effects of the crescent moon. Okay, but let's not lose the fact that we have this example of ancient peoples correlating celestial phenomenon with everyday phenomenon. In this case, seasons in their part of the world. What about the names of the week? Well, they're primarily named after planets. Planets, the moon, and the sun. Okay, so we have some good examples here. Right, we've got Sunday, right? Moon for Moon Day, which is changed to Monday, right? We've got Saturn for Saturday, so clearly, right? Now in English, we also have the rest of them, Tuesday, Wednesday, Thursday, Friday, which are actually named after Germanic gods. You can think of them as Norse gods, Thor, Freya, Woden, and Tyr. But most other languages stuck with the Greek names and left the days of the week named after planets. Mardi, Mercredi, my French is terrible, Judy, and Vendredi. Okay? Probably should have attempted the Spanish ones. Okay? If there was another planet that was visible to the naked eye, we would probably have another day of the week. Because clearly, the days of the week cover all the easily visible celestial objects that aren't stars. Okay, well you might be like, well, hold on, there's Uranus. Okay, well Uranus is not visible to the naked eye. Okay, not in a reliable way. Now, I mean, could you maybe spot it? Nah, that's a stretch. I mean, so you only need a really low power telescope or a pair of binoculars to see Uranus, but you can't really see it with the naked eye. Okay? And Neptune, you need a powerful telescope to see. So those planets were unknown, thus no days of the week named after them. Okay? All right, here's an example of an Egyptian obelisk. Okay, the shadow tells time. Okay, so the direction of the shadow tells the time of the day. It's the sun clock. Okay, here we have a structure that was built around celestial events like the summer solstice. This is Stonehenge, right? Very famous. Okay, from 1550 BC. Right, so over 3,000 years ago, over 3,500 years ago. Okay, here's further examples of the significance of the sun rising directly over the heel stone on the summer solstice. And the heel stone is this giant stone right here. Right? Other celestial events, other like the equinoxes and other solstices line up with other events. All right? So you can just see the importance of this big stone structure. All right? Here we have a temple to the sun in Mexico. All right. Here we have other examples of structures aligned directly with north-south. Okay. In order to be directly aligned with north-south in, New Mexico requires a pretty good understanding of the path of the sun and the moon through the sky, because as you know, the sun only rises directly in the east and sets directly in the west on one day of the year. I almost said the solstice, but the equinox. Well, it means you have to really be paying attention to the exact location in order to align something due north and south, because the Anasazi did not have magnetic compasses, so finding north and south was not as easy as it is for us today. Okay, here we have a sun dagger that marks the summer solstice based on the way the light comes in through cave paintings, okay, in the southwest United States. Pretty cool. In Peru, lines and patterns were aligned with paths of the stars. These are famous lines dug into the plains of Peru, the high plains of Peru, because on the ground they're completely underwhelming, but they look beautiful and well-defined from the sky. People like to say, well, that's because they were built for aliens. No, it's just they were built by people who have a sense of imagination and can imagine what they would have looked like from the sky, even though obviously the people that built them had no way of getting to the sky, no balloons, no airplanes, but they still had a sense of imagination, and they were still able to align things with paths of stars because they tracked them over the years. All right? Other examples, such as Machu Picchu, have structures that are aligned with the solstices, as Machu Picchu had a lot of religious significance, and for the Inca people, the stars and tracking the stars and the sun, in the case of the solstices, was very important to them. Here we have an example of detailed understanding of ocean currents based on astronomy. So this is essentially a star map, okay? An example, a recreation of an ancient Polynesian star map. Okay, so quick summary here. Right, this is a very kind of introductory, quick run through, but lots of fun ideas to think about. How people for thousands of years have been spending a great deal of time and effort, year after year, generation after generation, studying the sky, whether it's the sun, the moon, the stars, or the paths of the planets. All right? It really resonates with humanity. We want to figure out what's going on up there. Okay? So we're now going to look at ancient Greek science. Okay, we have a lot of records from ancient Greece. They're well known in the Western world, as opposed to, say, ancient Chinese records. And it has a lot of direct paths that we can follow to other bodies of literature, bodies of knowledge that are known in the Western world. Okay? So that's why we tend to turn to the Greeks. But it certainly was a key moment in history. When the Greeks started using a very similar approach that we would call to the scientific method, saying that they had to come up with ideas that were testable, that were based on data, right? Not just making guesses and saying they were fact. All right. Okay, so here we have a artist's reconstruction of the Library of Alexandria. This is a famous library because it held such a huge body of knowledge. These are the reconstructions, artist reconstructions. This is actually the new Library of Alexandria, just kind of in honor of the original one. All right. So Greeks were the first people to make models, okay, that we know of, based on the records of Greeks, right? And this is over 2,000 years ago. So they started to try to understand the world in a detailed way by building models. Here's an example of a geocentric model from 400 BC. All right. So what are we looking at? Well, this is the idea of the planets, the moon, and the constellations all circling Earth. Okay? Because although the ancient Greeks thought the Earth was round, they did think the Earth was the center of the universe, thus the center of everything we could see in the sky. You can see some names here, like Solus. Now it is quite interesting, right? We can clearly see Luna, right? Because this is a recreation of the Greek model. That's why the text is not in the Greek alphabet. It's in, the Roman alphabet. And this was probably created much later. But here, so we have Luna. This is Mercury, but in Latin. And here we have Venus, but in Latin. Well, it makes sense that the Moon, Mercury, and Venus would all have been assumed to be closer to Earth in the incorrect geocentric model, because they all display behavior that can only be explained if they're closer to Earth than the Sun. So then the Sun would have been the fourth object to orbit Earth, which is so weird that the Sun is just some arbitrary satellite of Earth that happens to be the fourth one out. Where, of course, we know that's not true. The Sun is all important. It defines the entire solar system. It's 98% of the matter of the solar system. Okay? Everything else just leftover dust. Okay? So here's an example of a model and an experiment performed by a famous Greek philosopher and scientist named Aristotelian. Okay? And in 240 BC, he measured the circumference or diameter of Earth. Okay, amazing. Okay, no satellites, no fancy GPS. He was able to determine fairly accurately the size of Earth, and he'd assume it was a sphere. Okay, and he did that based on the path of light at two different locations that were a distance of 5,000 stadia. Okay, well, a stadia, we know based on records, corresponds to a certain number of miles or kilometers in today's units. Okay, so let's see. So, well, we know 250,000 stadia is about 42,000 kilometers, so that's your conversion there. Okay, but 5,000 stadia was a known different distance between two famous cities, Alexandria, the city of the library, and Syene. Okay, and by knowing that the distance between those two cities and measuring the different paths of light between the two, because look, in Syene, the sun was directly overhead. He was able to determine that by looking down a well. But up in Alexandria, if you take a look, the sun is not directly overhead because the light is taking a different path, right? It's more indirect, okay? And look, that means there's a shadow. There's a shadow in Alexandria, but no shadow in Syene. So then based on the height of the pillar, because it wasn't a person, but the height of the pillar in Alexandria and the length of the shadow, he was able to get the angle of the shadow at 7 degrees, which then had to correspond to the angle of the wedge, okay, think like a slice of pizza, that is the circumference of a circle that's a slice of the spherical planet Earth. Well, if 7% corresponds to this distance here, then 7 degrees, corresponds to that little slice there. This is called an arc length, by the way, this red line here. Then 360 degrees must correspond to the entire circumference. So that's how he was able to measure the circumference. And the properties of a circle, such as the fact that a circumference divided by 2 pi gives you a radius, were well known to the ancient Greeks. Well, there you go. The diameter, the radius, the circumference of Earth, even the volume, were all known by Aristotelian and other scientists or philosophers, whatever you want to call them, of that time. Okay? Was this information essentially lost for millennia up until the Renaissance in Europe in the 1500s? Yeah, it kind of was. Okay? But we now look back on ancient records and realize that this was known at the time, over 2,000 years ago. All right? So the underpinnings of the Greeks' geocentric model was that Earth was at the center of the universe and the heavens must be perfect. Okay? So that was a big assumption they had, right? They kind of had a blind spot there to the fact that the heavens actually follow the same rules that the ground on Earth does. That there's universal physics that applies to, rolling a ball across your table, dropping a grain of sand, splashing a rock in the water, and the moons of Jupiter, or the fusion process inside of our own sun that produces light. All these things are governed by a few fundamental rules that we call physics. Okay, that was not known to the Greeks. Okay, the ancient Greeks. All right. There were some things that were very difficult to explain. Now we mentioned this in the last lecture, so this is a good kind of just connection between the last. It was at the very end of the last lecture we talked about this idea of apparent retrograde motion, and we did because of all the topics we were covering in the last chapter. It was all about what do we see as we stand on Earth? How do we understand observing the sky? One thing you can observe in the sky is the path of planets. One thing about the path of planets is that they go backwards over a few weeks out of the year. Okay? Right? Instead of following a general path, always moving towards the west, they actually start drifting back towards the east. Okay? So now we know, and we discussed this in the last lecture, that that's due to the fact that Earth overlaps Mars, or Venus overlaps Earth, or Mercury overlaps Earth, or whatever. It's because the planets that are closer to the sun, in this example Earth, are faster than the planets that are further from the sun, and in this example Mars. Thus, as Earth has a faster speed, it will eventually catch up with Mars and pass it. As it does, we can imagine lines of sight like this. And if you imagine that line of sight and a projection of Mars on the fixed background of constellations, because they're not moving relative to us, then Mars appears to drift backwards as we pass Mars during 3, 4, and 5 in this figure. Stages 3, 4, and 5. Okay? So that's an idea that we now understand based on the heliocentric model. More on the heliocentric model in a minute. But did the ancient Greeks have a heliocentric model? No. They had that whole misguided geocentric model. So they had to explain apparent retrograde motion with something called the Ptolemaic model. Okay? Now last time we kind of just wrapped up the lecture by focusing on the fact that the Greeks were so convinced that apparent retrograde motion had to be caused by something else than Earth passing another planet, because Earth couldn't be moving, and one of the reasons, besides an assumption about the heavens being perfect, was that there was no measurable parallax of the stars. So review that idea of measurable parallax if that doesn't sound familiar to you. But here we're going to focus on some other ideas. Okay? So the Ptolemaic model was the model of the age. It was a model that persisted for 1,500 years. Okay? Because it was very good at predicting things, but it did have some very misguided ideas. One of the biggest, especially that we focus on now with our modern lens, is this idea that apparent retrograde motion was real. It was actually the planets going backwards, and it was because planets orbited Earth on a gray line such as this one, but then on top of that gray line, almost think of it as a gear spinning on another gear, was a smaller orbit of the planet, which was called it was a smaller circle. Yeah, so it's just a smaller circular orbit of the planet. So that's not what planets really do. planets orbit the sun, right? But this idea of planets having a secondary orbit around some empty spot, because these gray dots, there's nothing there. It's just empty space. Well, that did explain the phenomena. But it doesn't follow one of the hallmarks of science that we'll discuss later, because it's not the simplest explanation. It's a rather complicated explanation that demands more questions. Because sure, it works. It explains apparent retrograde motion, but it demands the question of why. Why would planets do this? Why would they have this secondary circular motion on top of the original circular motion around Earth? Right? What's causing that? What force, to use the language of physics of more modern eras, what force is pulling the planet around this empty dot in the middle? Okay? Well, there's actually no good explanation. That's why a model like this had to eventually be rejected. Okay? So which of the following is not a fundamental difference between the geocentric and sun-centered models of the solar system? Take a moment, read these options. See if you have an answer. It's a good chance. Right? If you're falling asleep during the lecture, wake up now, read your options, see what seems best. Okay? The correct answer is the geocentric model is useless for predicting planetary positions in the sky, while even the earliest sun-centered models worked almost perfectly. Okay? That is not an actual difference between the two. Okay? Quick summary here. Okay, so now we're going to get to the point where we can really say modern astronomy began. Okay? So, we have Copernicus, Tycho, and Kepler, and they changed the Earth-centered model. How so? Okay? So we can really start with Copernicus, both in time frame and idea. Okay? So Copernicus, who lived from the late 1400s to the mid 1500s, or the 15th century to the 16th century, proposed a sun-centered model. Okay? Was he the first? No, but he was definitely at a key point where a model like this would have been accepted. He was respected. He published his ideas. Okay? He used the model to determine the layout of the solar system, planetary distances in astronomical units. Okay? But his model was no more accurate, so it wasn't winning anyone over in terms of accuracy. The Ptolemaic model was still just as good at predicting, so there was a lack of kind of concrete proof. Okay? That means that his model, his sun-centered model, did not get immediate traction. Okay? One problem about his model, and we'll discuss this in just a minute, was it still used perfect circles. Why was that a problem? Well, you'll see. Okay? So now on to a man that lived from the mid-1500s right up to the turn of the century that began the 1600s. Okay? So notice, right, that this man, his name, by the way, is Tycho, or Tycho Brahe, was born just a couple years after Copernicus died. So you can think of him as kind of the next generation. Was he a scientist? Not so much. He was more of an eccentric and a wealthy eccentric. Okay? But what he did is he compiled the most accurate naked eye measurements ever made of planetary positions. Tracked Mars, Venus, Mercury in a way that was unprecedented at the time. Right? Carefully cataloging all of his data from many, many nights of standing on the roof of his chateau or in his many, expensive homes, observing this data. Okay? But was he able to detect stellar parallax? Sadly, no. Okay? He was not able to. And remember, stellar parallax is the idea that if the Earth is really moving, which would certainly support old Copernicus's model, then the stars got to be shifting, right? Because if we're really moving, then we're moving a lot. Now we know it's 300 million kilometers from one side of the sun to the other side during, relative to our own orbit. Then this, stars shifting back and forth. Well, that's the thing. They only shift a tiny amount. Okay? The smallest shift is less than 1 arc minute. Okay? And if you remember, an arc minute is taking the 180 degrees from horizon to horizon and splitting every single one of those 180 degrees into 60 little segments, which is called an arc minute. Well, it turns out that the biggest shift of any star, of the 9,000 stars you can see with the naked eye, only shifts a little bit less than 1 arc minute. So first of all, it'd be slightly less than his level of accuracy, which still means maybe he could have seen it, but he's got to find just the right star. Okay? The name of the star is called Alpha Proxima. Okay, closest star to us. He probably didn't find it. Okay, because all the stars he looked at had no shift. Okay. So he still thought that the Earth must be the center of the solar system. He died thinking that the geocentric models had to be right. It's just, and it wasn't wrong of him to think that, because there was just no compelling evidence suggesting that the heliocentric model of Copernicus, the idea that the sun was the center of the solar system, was correct. It just wasn't coming into view. The data was not supporting it. Okay? Was he stubborn? Not necessarily. No, he just was following the data that he collected. That's the best we can really do as scientists, as thinkers. However, he did one particularly great thing besides collecting all this data. He hired a man called Kepler. And Kepler used Tycho's observations to discover the truth about planetary motion. So let's move on to this man, Kepler. Okay? So you can see Kepler was younger than Tycho. He was hired as an apprentice. Okay? Lived from 1571, died some 29 years after Tycho. He actually inherited all of the data. Okay? So it was passed on to him after his death. Kepler came from modest means, so he was not a wealthy eccentric like Tycho, but he was, from all accounts, a very brilliant man. And what he did was he tried to match all that data from Tycho Brahe with circular orbits. But he realized it just didn't work. There was an 8 arc-minute discrepancy. And he eventually decided to go with an idea that orbits were ellipses. Now, an ellipse is a mathematical term of a sort of elongated circle with some specific parameters to define it, as opposed to an oblong, which is like an egg shape. And it's because ellipses still have symmetry about 2 axes. We'll mention them a little bit more in just a minute. But the reason he probably was able to arrive at the idea of elliptical orbits was because he had such a strong foundation in mathematics. He was a mathematician. Okay? Tycho Brahe was not. Here's a quote from him. If I had believed that we could ignore these 8 minutes of arc, okay, that's a discrepancy, I would have patched up my hypothesis accordingly. Yeah, right? Because if there's just some strange phenomenon and it just seems to be just some error in the measurement, then yeah, it shouldn't shatter previous hypotheses or theories. Okay? But he couldn't explain it away. But since it was not permissible to ignore, those 8 minutes pointed the road to a complete reformation in astronomy. So he ended up coming back around almost, if you look at it, right? Almost 100 years after the publication to the idea of a geocentric model. Okay? So, what is an ellipse? So we talk about it. Okay? So an ellipse looks like an elongated circle. And it's symmetric about what's called its minor axis and its major axis. A good way to think of an ellipse is imagine 2 nails and a string that is held taut by a pin, and then tracing the line that the taut string naturally forces you to trace. All right? If you were to put those 2 nails on top of each other, or just replace them with a single nail, then of course what you would draw is a circle. See? But if they're not right on top of each other, if the 2 nails are apart, then the traced path is an ellipse. All right? And you can have eccentricity in ellipses. Not eccentric like Tycho Brahe, just being a weird guy that kept farm animals inside of his mansions, but instead eccentric in the sense that it's elongated. Because we say that a perfect circle is actually a type of ellipse, but with an eccentricity of 0. Most of the time we just call them circles. But anything that's not a perfect circle has eccentricity. In this case, moderate eccentricity, because it's only slightly elongated, or high or highly eccentric because it's very elongated. Okay? So hopefully that makes sense. And that directly takes us into Kepler's first law. Because after his big revelation and working with all that data, Kepler came up with 3 laws that we can still follow today. Okay? Now the first of Kepler's laws is that all orbits of planets around the sun are ellipses. Okay? Now it turns out that applies to orbits around other bodies. So all orbits of the moons of Jupiter are ellipses. But in this case, Kepler was just sticking to what he knew best, and that was planets. Okay? All right, and the sun is at one focus. Because the thing about an ellipse is those nails I mentioned that held the string in the previous slide, those are called foci, just the plural of focus. And the sun is always at one of the foci. And there's nothing at the other one. So here's an example of a planet right here that has a maybe moderate, maybe highly eccentric orbit, all right, around the sun. And in doing so, we can clearly see that it's not a perfect circle. We can clearly see that sometimes the planet is closer to the sun, sometimes the planet is further away, and the sun lies along the semi-major axis of the ellipse. Got it? Okay? Because the semi-minor axis just runs through the middle, and the foci are not on the semi-minor axis. That actually means that the semi-major axis is by far the most important when we talk about ellipses. Okay? You almost never hear anyone talk about the semi-minor. The terms for when a planet is closest to the sun is perihelion, helion for sun, and the term when a planet is furthest from the sun, it's aphelion. Okay? Those are just the special terms. You need to know those. Kepler's second law states that as the planet moves around its orbit, it sweeps out equal areas in equal time. This is another way of saying that when the planet is closest to the sun, it moves faster, and when it's further away, it moves slower. But it turns out that another way to say that is that this shaded area here is exactly equal to this shaded area here. Okay? One's obviously much more stretched out, one's quite squat, but they're the same areas. That's because the time to go from here to here, so the time to go to there is the same as the time to go from here to here. Because going from point 3 to point 4 is a path where the planet is moving very fast relative to when it's going from point 1 to point 2, where it's further from the sun and has slowed down. Okay? That's Kepler's second law. Kepler's third law, the one that gets used the most, states that there's a direct mathematical relationship between the period of a planet's orbit and its distance from the sun. Okay? And it turns out that the relationship is it's the period squared is exactly equal to the semi-major axis cubed. All right? So orbital period has to be in years, very important. And A, which again is semi-major axis, or it can just be thought of as average distance. Both are fine ways to think about it. Okay? Semi-major axis is more accurate and technical. Average distance gets the job done. Well, average distance must be measured in AU. AU is the average distance of Earth from the sun. We've mentioned it before, but this is just a quick reminder. Okay? So this formula here only works for these particular units of years and AU, because really it's kind of a ratio comparing things to Earth. If we want a formula that's universal, that would allow us to predict the orbital periods of moons or planets around other stars other than our sun, then we need something that doesn't just use Kepler's laws and actually uses Newton's laws. But more on that later. That will actually be in the second video for this chapter. All right, here's a graphical version of Kepler's third law, showing that relationship between period squared and average distance cubed. Okay, here we see a linear relationship between the square of period. So notice that the values on this axis are orbital period squared, and then on the horizontal axis, it's average distance cubed. Okay, so when you compare the square to the cube, the relationship is linear. And this is just a zoom in on the rocky planets, Mercury, Venus, Earth, and Mars, because they're all so much closer. It's a big jump then to Jupiter and a much bigger jump to Saturn, because the gas giants end up being much, much further spaced out as we go into the distant solar system. Okay? Part of the reason we don't just fly space probes out there all the time. But if we were to compare the relationship without period cubed and distance, or excuse me, period squared and distance cubed, then we end up with a very different curve. Because instead of linear, instead of a line, a straight line, we end up with a curve. And that's because whenever you have a graph of things that involve squares and cubes, well, you should expect a curve rather than a line. Okay? So it's kind of good mathematical intuition that I think you will benefit from thinking about and having in this class. Okay? So far we've kind of mentioned a direct lineage between Copernicus, Tycho, and Kepler. And obviously it's a big simplification. It's not like these were the only people studying astronomy at the time. And on that point, there's other figures that we need to talk about. And one of those is Galileo. And eventually we'll talk about Newton as well. But Galileo is so crucial because what Galileo did was collect a body of evidence that really, really hurt the idea of the Earth-centered model of the universe. Okay? He ended up being excommunicated from the Catholic Church because he was so determined to collect this body of evidence and just throw it in the faces of these cardinals and the Pope ultimately. Okay? That was not well received. But what he did is he just showed all these examples. Some were more indirect evidence, behaviors. One was the fact that he was able to find moons around Jupiter, kind of questioning the idea that the heavens were perfect. He was able to show that there was craters on the moon, thus questioning the idea that the heavens were perfect. Okay? And how did he do this? How did he collect all of his data? Well, there's like one kind of common thread, and that was that he used a telescope. Okay? He wasn't the first inventor of a telescope, but he was a very, very talented technician, and he was able to acquire and refine telescopes right at the time that they were first becoming available to the world. Okay? And you can see that he lived from the mid-1500s to the mid-1600s. Okay? So kind of a contemporary of Kepler. Okay? Contemporary of Kepler. All right. So Galileo's experiments showed that objects in air would stay with Earth as it moves. Okay? Aristotle thought that all objects naturally come to rest, and Galileo showed that objects will stay in motion unless a force acts on them. Okay? This ultimately ended up being called Newton's first law because Newton kind of refined the idea. Maybe he stole it from Galileo, but really he refined it. Okay? Now, where does that come from? So far I was talking about Galileo using telescopes. That's all he did. Galileo is also famous for, he's famous for something that is anachronistic. That, in other words, not anachronistic, that's apocryphal. In other words, something that didn't actually happen. And that's this idea of dropping things off the Leaning Tower of Pisa and showing that they fall at the same rate. But regardless, false story or not, Galileo is famous for kind of exploring this idea that all objects experience the same acceleration unless they're acted on by air resistance. Okay? And so he was starting to form these ideas of universal laws of physics. Okay? And so that's kind of the first hint, or first time we've seen in the slide, that there's this marriage at this point in history between astronomy and physics. You can't separate one from the other. Okay? So, as I mentioned, Galileo really had some problems with the idea of heavenly perfection and was able to show things like sunspots on the sun, mountains and valleys on the moon, as well as craters. Okay? All right? What about parallax? Okay? Well, Galileo didn't directly measure parallax. That ended up requiring better telescopes than Galileo had. But he was able to come up with the idea that the Milky Way, that big smudge across the sky, was composed of stars. And in doing so, he came up with a good theory that if the Milky Way was composed of millions of stars, then perhaps stars were all very far away. Okay? So far away that we shouldn't actually expect them to display parallax at measurable angles, certainly to naked eye observation like Tycho Brahe was doing. Okay? So that was a big idea. That was a big idea that stars were much further away than had been previously thought. And the idea, the scale of stars is, I think, kind of best summarized by this. The closest star to Earth is so far away that if our entire solar system, including the outer solar system, was the size of a college campus, then the next solar system, also the size of a college campus, would be in New York. Okay? Now, solar system is a big thing, right? A huge, vast, hundreds of millions of kilometers of space. But when you condense it down to a college campus, there's an even larger, vaster, unimaginably vast expanse of just emptiness between our little island of solar system and the next one. Because between our solar system and the next one is just emptiness. Okay? Some very, very cool gas, a few molecules per cubic meter, but virtual emptiness. So that's the idea of not just the gap between everything in space, but also the huge distances between objects, between stars. Okay? Furthering on the idea of parallax and just overcoming the rejections of the heliocentric model of the time in the 1500s, and this is one of his big breakthroughs, Galileo's big breakthroughs, was able to discover, track, and record the moons of Jupiter. Okay? Not all of them, there's over 50 moons of Jupiter, but the big four, because it turns out there's 4 very large moons of Jupiter. One of the moons is so large, it's larger than the planet Mercury. Okay? Just a little bit larger. But these moons are actually visible to a telescope. Even like kind of a run-of-the-mill kind of home hobby telescope today, what's one of the easy things you can see with such a telescope. You can see the moons of Jupiter. Galileo was able to see them with his rudimentary early telescope. And they clearly orbit Jupiter. They don't orbit us. They don't orbit Earth. Okay? And that's a big issue if you think that we're the center of everything. Okay? By the way, they're often called the Galilean moons because they were discovered by Galileo. And their names are Io, Ganymede, Callisto, and Europa. Okay? Okay? And then he was able to discover the phases of Venus. Now, based on the geocentric model, since Venus was closer to us than the sun, then Venus should have phases because it doesn't have the exact same period as the sun, but it should only have phases of new and crescent. Okay? Maybe even quarter, but never full. But it turns out that with a telescope, you can clearly see that Venus goes through a full set of phases, including full Venus and gibbous Venus. And that's only possible if Venus goes on the other side of the sun relative to us. Okay? So, as I mentioned, the Catholic Church ordered Galileo to recant. He said no. He was removed from the church. Okay? But eventually, the book was no longer banned in the early 1800s. They said, oh, okay, fine, we'll not officially ban the book anymore. Guess some librarian probably said, hey, we should, right? Catholic Church moved slowly, right? Took 200 years. But here's the most remarkable thing. He was only formally vindicated. I guess, that's probably a hard thing for them to do. But he was formally vindicated in 1992. They finally said, we excommunicated Galileo by mistake. The Catholic Church did. Okay, so a quick summary about the history. Kepler's laws, Copernicus, Tycho, and Kepler, right? Kind of culminating in Kepler. Kepler is the most important. His 3 laws, mentioned them in some depth. And then what was Galileo's role to play? Right, so the last thing I want to do with this video is talk a little bit about the hallmarks of science. I'm just going to kind of go through this with a good clip. There's not as much to say. How can we distinguish science from non-science, and what is a scientific theory? So defining science can be surprisingly difficult. Science from the Latin scientia, meaning knowledge, but not all knowledge comes from science. Okay? Here's the scientific method. It is idealized. It often does not work as cleanly as this. Do remember that a hypothesis is an educated guess, right? So when you say you have a hypothesis and it's not an educated guess, it's just a guess, okay? When you say you have a theory, you often mean you have a hypothesis in everyday language, okay? But that's okay. Everyday language can be different from formal language. But science rarely proceeds in this idealized way. For example, sometimes we start by just looking, right? Just observation can lead to big breakthroughs, right? Sometimes we follow our intuition rather than a particular line of evidence. We don't have to have the question first. We can just kind of look for inspiration to find the question. That's totally okay, right? You just can't make wild assumptions within that process, okay? So what are the big hallmarks? So the reason I want to talk about hallmarks rather than the scientific method is I think it encompasses more of the general idea of what science is. So hallmark number 1, Modern science seeks explanations for observed phenomenon that rely solely on natural causes. Okay? So you can't say divine intervention. You can't say mysterious creatures that we can't understand from the other side of the void, right? You can't have things that are just unknowable, unexplainable, all right? So inherently, religious explanations cannot fall under acceptable explanations for science, okay? Not that religion is bad, it's just not science, okay? Hallmark number 2. Science progresses through the creation and testing of models of nature that explain the observations as simply as possible. This is often called Occam's razor. Occam was a kind of 10th century monk that popularized this idea that the simplest explanation is usually the right one. And the idea there is that we should always strive for, within science, the simplest explanation. That's why the Ptolemaic model with the circles upon circles to explain apparent retrograde motion, well, did it follow Occam's razor? It did not, okay? Because that was a more complicated model. Had they just accepted the heliocentric model, it would have been simpler. It would have explained the same behavior with less rules. Okay? And that's the way you have to go. You have to ask yourself, is there another model that explains the same behavior with less rules? Because there is, then you need to seriously pursue that other model. Okay? That's science. Hallmark number 3. A scientific model must make testable predictions about natural phenomena that would force us to revise or abandon the model if the predictions do not agree with observations. So you cannot come up with predictions that are untestable. So you can't say, well, I think it's because planets are made out of supersauce, and the thing about supersauce is you can never measure it directly. Well, that's an untestable prediction. You can't do that, okay? It's a really dumb one that I came up with, but the idea, you can't make untestable predictions. They have to be testable, and ideally they have to be testable with current methods. Now sometimes we come up with predictions and say, okay, well we don't currently have the technology to test this, but maybe we will in 20 years or a generation, so but that, will still, that obviously gets pushed back, and that's okay, it should. But we still always have to strive for testability with current technical methods, okay? So, a scientific theory, unlike a hypothesis, is built on a big body of evidence, okay? Supported by a large, compelling body of evidence, all right? And it must not fail any tests. If a crucial test, if a body of evidence or an experiment really creates some contradiction to a theory, but that theory's been around for 150 years and is really widely respected, well, it doesn't matter, okay? You have to say, okay, well, it looks like our theory was wrong. And that happens. Big theories get rejected, okay? Even things like we'll talk about in the next lecture video, like the theory of universal gravitation by Newton eventually got rejected, okay, by Einstein. Einstein's theory replaced it. Many terms used in science have different or more specific meanings than they do in everyday language. I mentioned that, how, we in everyday language say, oh, I have a theory about something, but you really mean a hypothesis, okay? And again, I'm not saying you have to change the way you talk, but it's good to know that the words have different meaning in different contexts, right? Just like medical terms have different meanings, with a hospital staff than they might do when we're just using that term in everyday life, okay? So Darwin's theory of evolution by natural selection meets all the criteria of a scientific theory. This means what? Read the options. Make sure you have a confident answer here. Pause the video if you need to. Okay, there we go. After more than 100 years of testing, Darwin's theory stands stronger than ever, having successfully met every scientific challenge to its validity. Okay, that's crucial. It has to. Theories should always be pushed against. We should always be trying to disprove theories. That's what good science is about. All right, so quick summary about what science is. All right, and then quick note about astrology, that it's not science. Okay, I'm skipping over this for now. All right, now we're going to wrap this up on our next video, where I'm going to start with the fact and theory of gravity. This concludes the first video lecture for Chapter 3. Please check out the second one as well, where we'll talk about Newton, the theory of gravity, and a little bit of a crash course in physics. Okay? All right, so I'll see you all then. Thank you so much for watching this lecture video.